Hi there, and welcome back to Complex Analysis for Shut-ins. Today we're going to be talking about a rule for the derivative of an inverse function. We've done most of the derivative rules already, the sum rule, the difference rule, the product and quotient rules, and the chain rule, which turned out to be a little bit more complicated than we expected. And now we're going to do a generalization to the complex case of a familiar rule from Calc 1 or 2, in which we predict the derivative of an inverse function. Now, this theorem is going to be phrased fairly carefully because the functions don't actually have to be inverse functions. We intend to apply this to square and square root, to log and the exponential function, but these functions don't exactly have to be inverse functions, and so I want you to look closely at the hypotheses here. So first of all, we have two functions, f and g, of course, and we have the formula f of g of z equals z. Now, isn't that the formula for the inverse function? Why am I saying they don't have to be inverse functions? I'm not assuming that g of f of z is also equal to z. And it's possible that we would have one of these, but not the other. And so this is slightly weaker than saying that f and g are inverse functions. What we're saying, to be exact, is that f is the left inverse function of g, and g is the right inverse function of f. This equation, f of g of z is assumed for all z in some open subset of the complex plane. And we have one more kind of technical and surprising assumption here. You would think that that inverse equation would be enough, but it's not. We need to also assume that g is continuous at some given point z, and then we can provide a formula for the derivative of the function g in terms of the derivative of the function f. And that formula is g prime of z is 1 over f prime of g of z. And now we have a caveat here, like we need to assume that f prime of g of z exists, because what if f is not differentiable, right? So we need to assume that f prime is differentiable where required. And we also need to assume that the division here, 1 divided by this unknown value, doesn't produce an error. That is, we need to presume also that g of z is a point where f is differentiable. And when you take the derivative f prime of g of z, then you don't get 0, so that you don't end up dividing by 0. So all of that is captured by the proviso here, provided the right-hand side exists. That sort of sums up everything that we require of that. So that's what we're going to prove. And here's a little diagram of it. The set g is here. The inner function g maps any point z to a point g of z, and then the function f maps every point back to itself after doing that. So that's what we're going to prove here. Now I want to give you, just like I did in the proof of the chain rule, I want to start with a not so good proof, because it's really informative, and it also is useful because it helps you remember the right statement for this theorem. Sometimes it can be a little bit difficult to remember, is this supposed to be g prime of f of z or f prime of g of z, or what's supposed to be going on here? So the bad proof at least gives you a mnemonic for how to remember this thing. So supposing you have this equation f of g of z equals z, and you want to try to write down what is the derivative of g prime. Well, one way to do that is to simply apply the chain rule. So I'm going to label this is a bad idea, and it will actually look like a pretty good idea at first, and then we'll have to critique it. So the bad idea is going to be, well, we're going to apply the chain rule. And what are we going to apply it to? We're going to apply it to both sides of the, well, to the derivative of the equation f of g of z equals z. Now, the derivative of z is really simple. That'll be 1, but and if you want a proof, that's because that's a linear function. We did the general case of the linear function. So then the chain rule applies to the left-hand side and gives us f prime of g of z times g prime of z. So that tells us that f prime of g of z times g prime of z is equal to 1. And now you can see where this is going. Just solve for g prime of z. So g prime of z is equal to 1 over f prime of g of z. Now, if you're being responsible about your algebra, you should worry about whether we just divided by 0. But don't worry, because the hypothesis of this theorem states that this right-hand side exists, which implicitly means that this thing is not 0. So I guess we didn't just divide by 0. So this looks actually pretty good. And it's very tempting to call this a proof of the inverse function of the formula for the derivative of an inverse function. In the context of a high school calculus course, this might be enough to say, but it's not actually a rigorous proof yet. And let's talk about why. It looks pretty good, right? You apply the chain rule, you get the answer. Well, let's remember the statement of the chain rule. So the derivative, so this is the statement of the chain rule. the derivative of f of g of z is f prime of g of z times g prime of z. That, of course, is the statement of the chain rule. But then there's a little bit of provided, right? So provided the right-hand side exists. So the chain rule is not going to tell us anything about the derivative of f of g of z if that right-hand side doesn't exist. Why should we be worried about that, right? I mean, here, clearly we solved for it, so it exists. No, wait a minute. We solved for it under the presumption that we had this equation, and this equation came from the chain rule as applied to this. So the moment we applied the chain rule, we were in this situation. The only thing we knew was that f of g of z was equal to z, and furthermore, g was continuous. We did not know at the moment we applied the chain rule that g prime of z even existed. And for that reason, the application of the chain rule is potentially wrong. Now, there's only really one thing that could go wrong here, and that is that g prime of z doesn't exist, in which case this equation is simply false, and solving for g prime of z doesn't help you prove that it exists because we're starting with a false equation, right? So if g prime of z doesn't exist, then this will lead you astray. On the other hand, if you have some reason to believe that g prime of z just exists, you don't know what its value is, but you just sort of think that it exists, or you have some solid reason to believe that it exists, then this step is actually correct to calculate the value of g prime of z. So if I could just add to this theorem, not only that g is continuous, but if its derivative exists, then this theorem would be correct. This proof would be a correct proof of this theorem. But I can't afford to do that, because what we're going to do is we're going to introduce a function f like z squared, and then we're going to introduce an inverse function like the square root of z. And we're going to want to calculate the derivative of the inverse function and know that it has that derivative, but we can't assume that the derivative exists until we have some calculation of it. So I won't, if I have to assume that the inner function is differentiable in order to apply this theorem, then this theorem is not really very useful. So here the error in this proof is the assumption that g prime exists. If we don't know that it exists, it's wrong to apply the chain rule. So that's kind of a bummer. However, the correct proof of this is not too far in spirit from the chain rule. And in fact, what we need to do in order to get this right is actually we're going to sort of copy out the relevant part of the proof of the chain rule. So what we're going to do is we are going to think about the limit of this function in the definition of the derivative. So let me make that more precise. So what we're going to do is we're going to take the derivative with respect to z of z, and we're going to say that's the same as the derivative with respect to z of f of g of z, right? This much is certainly true, right? And I have no worries that the derivative of f of g of z doesn't exist, for example, because f of g of z is the function z, and it is so these are the same thing, and they both will give us 1, right? So I know up front that f of g of z is differentiable. Now, it doesn't help me get the derivative of g, not exactly, not immediately, but I know up front that this is differentiable, and I know the definition of the derivative of that thing tells me that it is equal to the limit as w approaches z of f of g of w minus f of g of z over w minus z. So that's, that's from the definition of the derivative. So, so we know that that is the right representation of this. Now, what I'm going to do here is, just like in the proof of the chain rule, I'm going to multiply and divide by g of w over g of z. And I'm taking for granted that you've watched the chain rule video. And what you should be saying here is, now hold on just a minute, because that's not going to work. So if that's what you're saying, that's good news to me as your teacher. So here's what I'm going to do. I'm going to multiply by g of w over g of w minus g of z, and divide by g of w minus g of z, just like in the proof of the chain rule. Actually, to be precise, just like in the false start of the proof of the chain rule, before I explained why that stuff is not going to fly, right? So in that proof, we did exactly that, and I said, that is not going to really, that's not really going to work. And why? Why won't that work? Because maybe g of w minus g of z is 0. I mean, we don't need to worry that w minus z is 0 because the limit as w approaches z excludes the particular value w equals z. But we do need to worry that g of w minus g of z could be 0 even if w is not z. And then I just multiplied it and divided by 0, and that was exactly the problem that we had with that false start for the chain rule. Well, in this problem, we get away with it, and let's see why. If g of w would happen to be equal to g of z, then f of g of w would happen to be equal to f of g of z, which means that w would be z. This is not about the derivative. This is just about the fact that f and g are inverse functions in exactly this way. If g has a left inverse, then it has to be injective. So I'm going to note that over here. So note, well, let me say because g has a left inverse, g is injective. So I can even give you a proof because it's so easy. So if g of w equals g of z, then f of g of w equals f of g of z. So w equals z because f of g of w is w and f of g of z is z. So that's a simple little proof that g is injective. And that means that so long as w is not z, g of w will not be g of z. And so this step is now algebraically correct. It was dangerous and potentially incorrect in the proof of the chain rule, but in this particular context, this is correct. And this is really nice. This is what we want to look for. This thing looks like the limit that would give us g prime of z, which is what we eventually want to solve for. And this limit is actually going to give us the f prime of g of z. Why is this going to give us f prime of g of z? Well, this limit is going to behave exactly as it does in the proof of the chain rule. G of z is a constant. It's analogous to what we called alpha in the chain rule. I think it is the same thing that we called alpha in the chain rule. And this is a place, this is the value at which we are calculating a derivative if we are only doing this limit here. G of w is a variable, we can call it u, and this limit is then the composition of an outer function f of u minus f of alpha over u minus alpha with an inner function, which is g itself. And so using that logic, just as we did in the proof of the chain rule, we can demonstrate that this left-hand limit is actually equal to f prime of g of z. And would that it were that easy. The thing is, I've just made this argument in order to motivate where we're going with this proof. I've made this argument that the left-hand limit is f prime of g of z, and the right-hand limit is g prime of z. And I mean, that's kind of true. But the fact of the matter is we don't have two limits. We have a limit of a product. So if I want a left-hand limit that I can argue about on its, on its own, and a right-hand limit that I can argue about just for itself, then the only way I'm going to be in that situation is if I first apply the product law for limits. So really, I shouldn't yet be arguing about a left limit and a right limit as they're separate things because I haven't yet applied the product law for limits. I don't have a product of two different limits. I have a limit of a product. So if I wanted to make that argument, the right place for me to start is the product law for limits. Okay, but wait a minute. The product law for limits, just like the chain rule, says the following thing works provided the right-hand side exists. And the right-hand side is going to be the limit of this times the limit of this. It's going to have the definition of the derivative of g. Now, normally we're thrilled to see that, but in this problem, we're not thrilled to see that. If I apply the product law for limits, I'm implicitly assuming that that right-hand limit that I will get, the limit as w approaches z of g of w minus g of z over w minus z, I'm implicitly assuming that that thing must already be known to exist. And I don't have that assumption, not active, not now. I am not assuming that g prime of z even exists. So what are we going to do? Like, we can't split the limit and deal with them separately. The odd thing is I already know that this whole big huge limit exists. In fact, I know its value, it's 1, right? I started with that. So I'm kind of in a confusing situation here. If I had only the left-hand limit, I would be okay. I know that that exists and I know what it is. It's f prime of g of z. Look back at the proof of the chain rule if you're confused about why. So if I had only this, I could deal with it and say with confidence it's f prime of g of c. If I had only this limit, though, I don't even know that that exists. And if I have the limit of their product, then weirdly, I do know that that exists and I know its value and its value is 1. So what do? Well, we have to leverage the quotient law for limits to our advantage here. So what we need to do is we need to take this thing, this equation, 1 equals all of this, but I'm going to copy the 1 down. 1 is equal to this. We need to take this equation here and we need to divide it by the right thing on both sides and then apply the quotient law for limits. This will allow us to get in there and cancel what we need to cancel and get rid of things without assuming that the important limit of this problem already exists. So let me illustrate. So I'm going to have to take this up here. So I'm going to take both of these sides of this equation, this ugly equation, and I'm going to divide it by basically the thing I like, the left-hand limit. So here, 1 over the limit as w approaches z of f of g of w minus f of g of z over w minus z, that ugly thing is equal to, and now I get this entire thing, the limit as w approaches z of f of g of w minus f of g of z over g of w minus g of z. And then here I get finally g of w minus g of z. I'm not leaving myself room. So this is times, I'm going to have to rewrite it, sorry. So this is equal to the limit of fgw minus fgz over g of w minus g of z times g of w minus g of z over w minus z. Okay, so that is the big, huge limit that we've got. And then this thing also gets divided by the limit of the left-hand thing. So that's, again, the fgw minus fgz over gw minus gz. Okay, so this is the result of taking this big ugly equation and simply dividing it by a limit like this. Okay, divide both sides by that. Now, and then these two things, these are equal to each other, right? Now, just if you just look back at the proof of the chain rule, sorry, this is going to be, this is written wrong. This should be g of w minus g of z. So g of w minus g of z. Isn't this easy? So now this thing, just as in the proof of the chain rule, this you can just think of this as a constant g of z. It's a constant at which we are calculating a derivative. This is a composition, this is a limit of a composition of two functions, and we can evaluate it as such, and we get f prime of g of z. Just look back at the proof of the chain rule to see how that works. So this is 1 over f prime of g of z for the left-hand side. Now for the right-hand side, I mean, I could evaluate this denominator in the same way, but it wouldn't help. What I've got is a massive limit, which is the same as this one, which is known to exist as a product, but its individual parts are not known to exist. At least the right-hand part is not known to exist. And then divided by another massive limit, which is known to exist, okay? And it's known to be equal to f prime of g of z. Now, the quotient law for limits tells you that the limit of a quotient is equal to the quotient of the limits, provided that the two limits in that quotient both exist, and the one that has to go in the bottom is not 0. So basically, the quotient law for limits says the limit of a over b is lim a over lim b, provided both lim a and lim b exist, and lim b is not 0. So So what? So we know that this thing exists, this huge limit here, which is just a copy of this, exists because we know that it's equal to 1. And we know that this exists because for the same reason this does, we know what this limit is. And that means that we are actually in a position where we know all the hypotheses of the quotient law for limits. And so we can regard this quotient of limits to be a limit of a quotient, which will give us finally the cancellation that we need, right? When we kind of, in a sense, we're using the quotient law for limits backwards, if you will, although it's an equality, so there really is no backwards and forwards. But we're using it backwards to say, look, this quotient of limits is a limit of quotients. And so we can take this thing divided by that, and we can take the limit of this ugly thing divided by that ugly thing. But that ugly thing there was designed to cancel this one, and so we just end up with g of w minus g of z over w minus z, and everything else is gone. So this is the limit as w approaches z. So to recap, we have this huge limit, which is a product, and as such, it has a limit, which we know is 1. This denominator, we know that limit exists. The quotient law for limits applies and tells us that's equal to the limit of the ratio between them. And the ratio between them sees all this massive cancellation between these terms, which leaves us only with that. Now, what this says is that this thing, which is known to exist, is equal to this limit. What is that limit? That's the definition of the derivative. And so we conclude here that g prime of z exists and is equal to 1 over f prime of g of z. So that was really challenging, but important to do right. It's important to get the right reason why the derivative of this function not only equals this, assuming it exists, but exists under these conditions. So that is the derivative of the inverse function. Now, let me ask you an important question here, and I'd like you to think on it. We have assumed in this theorem that the function g is continuous at the point z. The important question for you to consider is, where in this proof did we use the fact that g is continuous at z? So think on that, and we'll answer that question in the next video.